Okay, this is the first test in the Shell year that you took in the first half term. It's about prime factorizations, factors, multiples, and square numbers and cube numbers. So with this one, it's a simple match exercise. If we begin by looking at the top row, an example of a prime number would be something like 3 or 2 or 5. Now a prime number is a number that can't be built by other numbers using multiplication and builds new numbers. So 3, for example, cannot be built, but it does build the number 9, which is 3 times 3. It also builds the number 27, which is 3 times 3 times 3. So it builds new numbers, but can't be built by other numbers. A composite number, an example of this is 6. Now, a composite number is built by other whole numbers or other primes. So 6, for example, is built by 3 times 2. An integer. An integer is a whole number, like 1, and it didn't say a positive integer, so we could have had something like -5 as well. A square number like 36. Now, it's a whole number whose prime factorization contains an even number of each prime. Okay, so for example, 36 is, its prime factorization is 2 times 2 times 3 times 3. Now, the reason it contains an even number of each prime is because then we can group it into 2 equal groups. So 36 is 2 times 3 times 2 times 3. Which is this, and what we've used there is the commutative law, and the brackets show the associative law of multiplication. So 2 times 3 times 2 times 3 is the same as 2 times 3 squared. So clearly 36 is a square number because it can be written as something, 2 times 3 squared. A factor. Well, 6 is a factor of 48. If we look at this in more detail, we'll show that it's a whole number whose prime factorization is contained within the other one. So 6 is 3 times 2. And its prime factorization is contained in 48, which is 2 times 2 times 2 times 3. You can see that 6, 2 times 3, is contained within the prime factorization of 48, 2 times 2 times 2 times 2 times 3. Okay, so this is the match-up exercise. If you understand how numbers are built using primes, it's fairly straightforward. Okay, so let's move on to question 2. Now, question 2 is a question about primality testing. How do you know if a number is prime or not? Now, there's no easy way to check if a number is prime or not. We just have to try and see if it's got any divisors, if anything goes into this number. We need a little bit of prerequisite knowledge here, which I'll go into now. So, factors of a number come in pairs. The pairs will have a big factor and a small factor. Example, 100. 100 has the factors or factor pairs 1 and 100, 2 and 50, 4 and 25, 5 and 20, and 10 pairs with itself. Now notice, apart from the number 10, that each pair, has a small factor and a big factor. Okay? So in 2 and 50, 2 is the small factor, 50 is the big factor. Notice how the small factor is less than the square root of 100, which is 10. So all the small factors are less than 10, and all the big factors, they are larger than 10. So 2 and 50, 2 is smaller than 10, 50 is larger than 10. Okay? 10 itself is neither a small factor or a big factor, it is just the square root. Let's look at another example which isn't a square number, like 120. Now 120, the square root is about 11. So 11 squared is 121, so square root of 120 is about 11, slightly smaller than 11. So 120 will have factor pairs. Each factor pair will have a small factor and a big factor. The small factor will be smaller than 11, and the large factor will be bigger than 11. So 1 and 120, that makes sense. 2 and 60, small factor, big factor. 3 and 40, small factor, big factor. 4 and 30, 5 and 24, 6 and 20, 8 and 15, and finally 10 and 12. So 10 is smaller than 11, 12 is bigger than 11, small factor, big factor. So this helps us with primality testing. So what our aim is in primality testing, to test whether a number is prime, the method is to test the possible small factors. Okay? That is, the possible factors less than the square root. Okay? So that's what we're going to be looking. We're going to see if there are any factors less than the square root of 79, because factors come in pairs. So we don't need to test all the numbers, we just need to test the smaller factors, the ones less than the square root. So 79, the square root is about 9, because 9 squared is 81, so the square root of 79 is about 9. So let's test the possible small factors. 2 is a possible small factor, but it's not a factor because 79 is odd. 3 is a possible small factor, but we know to test whether a 3 is a factor, we can do the digit sum. We can add up the digits. The digit sum of 79 is 7 plus 9, which is 16. That's not divisible by 3, so 3 is not a factor. 4, is 4 a possible small factor? Well, no, 4 is not a possible small factor because 4 is built by the number 2, and since 2 is not a factor, 4 cannot be a factor. So 2 is not a factor, so 4 is not a factor. We don't even really need to test 4. Okay, we only really need to test the prime, the possible small factors which are prime, because we know that all other numbers are built by primes, so since 2 is not a factor, in this case 4 cannot be a factor of 79. 5, well, 79 does not end in a 0 or 5, so 5 is not a factor of 79. We don't need to test 6, because 2 and 3 are not factors, so 6 will not be a factor of 79. We do need to test 7, though, because 7 is prime. 7s into 79 go 11 times remainder 2, so it's not a factor. Leaves a remainder. Okay. Do we need to test 8? Well, 8 is built by 2s. 2 is not a factor, so 8 is not a factor. And we don't need to test 9, because 9 is bigger than the square root. Also, 9 is not prime, it's built by 3s. And since 3 is not a factor, 9 won't be a factor. So we've tested all the possible small factors, 2, 3, 5, and 7. Therefore, 79 must be prime. Okay, so this is primality testing. You test the possible small factors, which are the prime numbers less than the square root, because factors come in pairs. So this will help us to answer the next question, testing whether 143 is prime or composite. Composite means it's built, prime means it's not built, but builds new numbers. 143, well, we need to know its square roots. We know that the square root of 144 is 12, so the square root of 143 is slightly smaller than 12, about 12. Let's test the possible small factors, which are the primes less than the square root of 143. So 2 is a possible small factor, but it's not a factor because 143 is odd. What about 3? 3 is a possible small factor, but the digit sum is 1 plus 4 plus 3, which is 8, and 8 is not divisible by 3, so 3 is not a factor. 5 is not a factor because it doesn't end in 0 or 5, so 5 cannot be a factor. The next one we have to test is 7. 7s into 143, you just have to do the bus stop method. You could do the bus stop method for all the previous cases as well and show there's a remainder, but with 2, 3, 5 we have some nice easy divisibility tests. 7 doesn't have a nice divisibility test, so we just have to do it. 7s into 143 go 20, remainder 3, so it's not a factor. the next prime number after 7 is 11. 11 is smaller than 12, so we have to test it. Now, a common mistake with this question was not to test 11, even though you must test 11 because 12 is the square root and 11 is smaller than that. 11's into 143, go once, remainder 3 times. 11's into 33, go 3 times, with no remainder. So, 11 builds 143 with 13. So 11 times 13 is 143. So 143 is composite because it's built by 2 primes, 11 and 13. Okay, so you didn't actually need to test 2, 3, 5, and 7 if you knew that 143 was just 11 times 13. Okay, but if you wanted to show it was prime, you had to divide 143 by 2, by 3, by 5, by 7, and by 11. And when you get to 11, you realise that actually it must be composite because 11 is a factor of 143. And notice that we have a small factor, 11, and a big factor, 13, since 11 is smaller than the square root and 13 is bigger than the square root of 143. We shall move on to question 4. Okay, this is a basic methods question. Can you find the lowest common multiple of 2 numbers? Well, to do that, let's write down the prime factorizations, one above the other, and line up the common primes. So the common primes, let's line up one of the 2's, one of the 3's, and the 7 isn't common. Okay, so the lowest common multiple, we just write down one number for each column. So here we have a 2, then we have 2 shared 2, so we just write one of them, and we have a shared 3, so we just write one of them, and a 7. So this number here, which is 168, is the lowest common multiple. It's the lowest common multiple because it's the smallest number which contains 24, there's the number 24, and it also contains number 42, there's the number 42. Now if you look here, if you do a Venn diagram method, what I've effectively drawn is a Venn diagram. 168 is the smallest number which contains both the prime factorizations of 24 and 42. You cannot find a smaller one. You can find larger numbers that contain 24 and 42, but you cannot find a smaller number. You cannot find a smaller number than 168, which contains 2, 2, 2, 3, and 7. If you tried to get rid of one of those numbers, any one of those numbers, 2, 2, 2, 3, and 7, that would mean that this new number would not be a multiple of either 24 or possibly 42. So if I got rid of the first 2, for example, now I don't have 24 in the prime factorization of this new number. Okay, let's move on to the next question. So 784, find its square root using prime factorization. 784, we can write down its prime factorization. Let's do the A method here. Let's break it down into 2 times 392. I then can break down 392 into 2 times 196. I can break 196 down into 2 times 98. I can then break 98 down into 2 times 49. And I can finally break 49 down into 7 times 7. So what I've done there is I've broken down 784 into its prime factorization. Okay, 784 I could rewrite using the commutative law as 2 times 2 times 7 times 2 times 2 times 7. Now what I've effectively done there is split it into 2 groups. Since I've split it into 2 groups, this is the same as writing the group times by itself or writing the group squared. So 784 is 2 times 2 times 7 times 2 times 2 times 7, which is 2 times 2 times 7, all squared. Okay, this means that I can square root it. So square root of 784 is really just the square root of 2 times 2 times 7 squared, which is just 2 times 2 times 7. And we can work out what 2 times 2 times 7, it's 28. So the square root of 784 using this prime factorization method is 28. Okay, next. we're going to be looking at explaining why is 78 a factor of 1170, or why is 1170 rather a multiple of 78? Well, a simple sentence will suffice. 1170 contains 2 times 3 times 13. So you can see that 1170 contains that product 2 times 3 times 13. And since it contains 2 times 3 times 13, which is equal to 78, then it must be a multiple of 78. So why is it a multiple? Because it contains 2 times 3 times 13, which is equal to 78. Okay, question 2. Explain why this number is a square number but not a cube number. Well, a simple sentence will suffice again. The prime factors, or the prime factorization rather, of 5,184, it can be split into two equal groups, but it can't be split into 3 equal groups. Okay, so I'll go into a little bit more detail here. So it can be split into 2 equal groups, so 5,184 could be written as 2 cubed times 3 squared times 2 cubed times 3 squared. So I've just broken up the number, or I've used the commutative law there to rearrange how I'm multiplying these things, remembering that the index signals how many 2's I have. So in 5184, I've got 2 to the 6, which is 2 times 2 times 2 times 2 times 2 times 2, or 6 2's. And 3 to the 4 is 3 times 3 times 3 times 3, which is 3 times by itself 4 times. So I could rewrite this as 2 cubed times 3 squared times 2 cubed times 3 squared. Okay, check that you agree with that. I could put brackets around the group and write it times by itself. So it's a square number. It can be split into 2 equal groups, so it's a square number. If you try to split it into 3 groups to make it a cube number, you'll be left with the following situation. You could have split the 2's up into 3 equal groups and try and split the 3's up, but you get this extra 3 at the end because there are 4 of them, and they can't be put into 3 equal groups. So it's definitely not a cube number. So there's my 3 groups and this 1 3 left over at the end. Okay, let's look at the next question. Explain why 15 is not the highest common factor of 720 and 1,575. Well, it's not the highest common factor because 720 and 1,575 share 2 common 3's and a common 5. So 3 squared times 5, or 3 times 3 times 5, which is 45, is a higher common factor, higher than 15. So we found a common factor which is higher. In fact, 45 is the highest common factor. So this means that 15 is not the highest common factor because I just found a higher one, 45. Okay, let's look at the more challenging problem-solving type questions. I'll try and explain these in some detail. These are quite tricky and require a really strong understanding of the methods of finding highest common factors and lowest common multiples. So, to do this, we're going to need all the prime factorizations of the numbers we're given. Let's do 126. We could break this down into 2 times 63, which is 2 times 3 times 21. 21 can be broken down into 3 times 7. That's its prime factorization, 2 times 3 times 3 times 7. Okay, let's write down A and 21, one above the other. We need 21's prime factorization, which is 3 times 7. And underneath, we'll write 126. Okay, so we've lined up the final 3 and the 7. So, what numbers must A contain? Well, it must definitely have a 2. It must definitely have a 3. But it can't just have 1 3. Otherwise, I would have had to have lined up the 2 3's and only written 1 3, the shared 3 in the lowest common multiple. So I need an extra 3. So this number, 2 times 3 times 3, is the smallest possible number which when paired with 21 will give me a lowest common multiple of 126. I mean, I could also put in a 7 in this number for A, but that would be bigger, and I want the smallest possible number for A. Okay, so this number here is 18. Now, a common mistake when answering this question was to assume that 6 would work, but 6 does not work, because if we were to write it using our methods for finding lowest common multiples, we would have to line up these 3's, and the lowest common multiple would be 2 times 3 times 7, which is the LCM, and this number is 42, and it is not 126. So 6 does not work for A. You have to have this extra 3 to give you the lowest common multiple, 126. So the answer for this question was 18. Question 2, from the problem-solving section. So we want two possible numbers, any two, that have a lowest common multiple of 120 and a highest common factor of 4. So let's find the prime factorizations, since if we know how the numbers were built, we can work out everything we need to know about the two numbers we're trying to find. Okay, so we'll break it down. 2 times 2 times 30, 2 times 2 times 2 times 15, and then break 15 down into 3 times 5. So this is the prime factorization of 120. 4, the prime factorization is just 2 times 2. Let's choose two numbers A and B. Okay, so we know that they must have two 2's in common, and only two 2's in common, since their highest common factor is 4, 2 times 2. So, the lowest common multiple, 2 times 2 times 2 times 3 times 5, well, we've already written the 2 times 2 part. So now we need to spread out the final 2 times 3 times 5 amongst A and B. Okay? So I could just write them all next to A. So that would be one possible pair whose HCF, highest common factor, is 4, and whose lowest common multiple is 120. This is not the only answer, it's one of the answers. Let's look at the other possible answers. Well, I must again have the 2 times 2 and the 2 times 2 because that's the highest common factor, and then I must spread the 2 times 3 times 5 amongst the other numbers. So that's another possible answer. I could do the same thing again. I just move where I put that final 2, 3 and 5, and I could write it like this. That's two other numbers whose HCF is 4 and whose LCM is 120, and there is one more possible answer, and that is just this one here. So they are all the possible answers. Okay. All of these values for A and B have an HCF of 4 and a lowest common multiple of 120. So that was the method for this question. You only needed one of those possible answers, but they are all of them just for your benefit.